Welcome to 5G Technology World. I'm Site Editor Martin Rowe. At the 2020 International Microwave Symposium, the 5G Summit had a common theme that ran through every talk, and that had to do with efficiency and power and heat. One of those speakers, Naveen Yanduru, Vice President and General Manager at Renaissance Electronics, gave a talk about sub-6 gigahertz and millimeter wave RFICs for 5G wireless infrastructure RF front ends. In that talk, he spent a considerable amount of time talking about heat and the fact that we need innovation to overcome the heat problems, the efficiency problems that occur in 5G transmitters, not only at macro cells and small cells, but in handsets and user equipment as well. You talked about power amplifier inefficiencies. Can you tell us, is that an ongoing problem, or did it something that has emerged with the design, the development of 5G?
Yeah, thanks, Martin. I think that's a very fundamental question in the sense the power amplifiers play a big role in setting the efficiency of transmit chains in the radio transmitters of 4G as well as 5G. Fundamentally, as you may know, a power amplifier can be classified as a large signal amplifier. So when you have an amplifier with a fixed supply and you have the signal amplitude varying, because that's the nature of most of the amplitude modulated signal waveforms in LTE as well as in 5G, then the efficiency keeps varying. When the signal amplitude is at its maximum or when it is at the peak, you get decent efficiency close to the saturation efficiency, like we like to call. But when the signal amplitude goes further down from its maximum peak value, then its efficiency starts falling. So as an overall effect, when you see that the average power that is going through the power amplifier is much lower than the peak power that the power amplifier can support, your overall efficiency of the power amplifier will suffer. And there are some mitigation circuit ideas, such as you may know, class AB architectures that people use while still keeping some linearity to improve the efficiency somewhat, and a little bit more complicated techniques like load modulation and supply modulation, which come there with their own baggage. But still, even as you throw all of these ideas at it, the power amplifier efficiency seems to be one of the biggest bottlenecks in radio transmitters for 4G, 5G, and beyond.
What problems occur as a result of PA inefficiency?
That's a very good question. The bottlenecks are twofold, in my opinion. The first bottleneck is the fact that the pure efficiency of what the signal you're transmitting that you can get. You do not want to dissipate too much power while getting only so much signal power out of your antenna, which makes your battery to discharge much faster when you're talking about a mobile handset, or even in a small cell or in a macro station. You don't want to use up too much power from the grid, right? But the bigger problem, however, comes with the heat that you dissipate with the additional power that you take in order to put the transmitted power out of your antenna. So even as the data rate is not compromised, you can push out the data rate because you have very good amplitude modulation and signal bandwidths that you have. But to be able to get the data rate out, your efficiency starts degrading, which impacts both the amount of power that you use as well as the thermal issues associated with it.
Do inefficiency problems occur at sub-6 gigahertz frequencies, FR1, at millimeter wave frequencies, FR2, or both?
That's a very good question as well. As a matter of fact, it happens at both, what we call as FR1, which is the sub-6 or the sub-7 gigahertz application, as well as in the FR2, which we like to call as the millimeter wave applications. And at FR1, the problem's a little bit different because the amount of output power that you're transmitting is much higher in FR1, and normally what it means is that the overall power that you're dissipating is also higher. FR2 comes with its own challenges because the frequency is much higher. So on a apple-to-apple basis, it's hard to get the same efficiency at higher frequencies that you may be able to get at sub-6 or FR1 frequencies. So even as maybe the total transmitted power is a little bit lower, because as you know, at FR2, we use a lot of beamforming to improve the antenna gain, but the problem is the higher frequencies normally come with a penalty in efficiency. And here at Renesas, at both FR1 and FR2, we have come up with a lot of techniques to improve the efficiency. For example, in our beamformer ICs that we have at FR2 frequency, we have one of the best efficiency in our transmit beamforming IC, while keeping very high dynamic range and phase and gain orthogonality to make the beamforming application work very well at these frequencies.
How is beamforming an issue with heat problems at both FR1 and FR2 frequencies?
Beamforming, as you know, we could talk about beamforming in two contexts, right? There is what we call as a digital beamforming, or where we have a situation where each element in the antenna get its own pre-coding. And the other beamforming that we call as a hybrid or the analog beamforming, which is normally deployed right now in FR2 frequencies. So beamforming as such is not going to directly impact efficiency of the power amplifier, as the power amplifier itself is a circuit block, and it comes with its own efficiency depending upon some of the constraints and circuit limitations that we have discussed earlier with respect to fixed supply. But beamforming can make it a little bit more complicated sometimes, because if you're talking about digital beamforming, then we need a particular signal chain to support each antenna element. Unlike when you would not have a beamforming situation, then you would have one big honking PA along with its driving circuitry push into a big antenna. But now, because of beamforming, you have a lot of these antenna elements, and each of the antenna elements does not only have its own PA, but also the downstream circuitry like the pre-drivers, the transceivers, and the data converters. So overall, because of this multiplicity of the driving circuitry, the overall efficiency in a beamforming application starts to get impacted, as we have noted. Now in FR2 frequencies, where we are using hybrid beamforming, this particular situation is mitigated to some extent because hybrid beamforming, you do not have a full chain of signal for the entire beamforming element. Instead, some of the beamforming or multiplicity is just done in the analog and in the RF domain, reducing the number of DACs, for example, that you need in a hybrid beamforming compared to digital beamforming. And this is imperative, and especially in FR2 frequencies, to manage this overall heat and efficiency issue. Ideally, you would do a complete digital beamforming in FR2 frequencies as well. But again, that would mean even larger impact to the overall heat issues, as well as, of course, the cost issues. So that's why in FR2 of 5G right now, we are limiting it to mostly hybrid beamforming techniques because of the limitation of the heat as well as the cost and the overall power consumption.
Is power amplifier heat a problem with macro cells, small cells, user equipment, or all of the above?
And the simple answer again is all of the above. Different problems at different levels, right? If you take the case of the user equipment, the amount of power that you are transmitting is much lower, because in the user equipment, you are only transmitting so much output power. But you have only so much surface area to dissipate your heat, and also the battery powering your system requires so much power before it starts to discharge very fast. So yes, even as the power that you're sending out in a handset application is much lower, it comes with own challenges because of the area restrictions where you can dissipate the heat and the limitations on the battery. On the flip side, if you go to, let us say, a small cell or even to a macro, the amount of power that you are transmitting starts to increase a lot. And in the outset, it looks like it's going to be a bigger problem because now you have to deal with more heat on a apple to apple basis. But what really happens is you have more tools at your disposal when you're talking about a small cell or a macro cell. You could use some kind of active cooling techniques where you could have fans to dissipate the power, and also you could use higher power supplies to able to eke out higher efficiencies in your power amplifiers, and also come up with complex architectures for your power amplifier, such as load modulation architectures and supply modulation architecture, also known as envelope tracking for the supply modulation, as you may know, which can help mitigate this to some extent, as well as the total area that you have to dissipate the heat. So the simple answer, rather the convoluted answer to your question is it depends, and each one has its own problem. But again, the simple answer is yes. The heat is a problem at all levels, whether it's a macro cell, a small cell, or a handset.
What can engineers do to improve efficiency in power amplifiers?
Yes, so this remains one of the biggest challenge, especially for RF and millimeter wave circuit designers. So at Renaissance, we have been spending a lot of time in innovating to improve the efficiencies both at FR1 and FR2, mainly for the infrastructure application and the small cell applications. At FR1, we have come up with a lot of IP that goes in and around the power amplifier to make the power amplifier more efficient. We like to call these as smart silicon innovations because we come from silicon background and we have a lot of ideas on how we can manage the signal and get the most out of the given figure of merit of a power amplifier, whether it is in gallium nitride technology or LDMOS technology, by wrapping a lot of our signal processing ideas around it through our pre-drivers, through our bias controllers and other techniques, while we are also looking directly at the power amplifier itself in gallium nitride to try and improve the efficiencies at FR1 frequencies. Just to give an idea, we strongly believe that by managing smartly using our signal processing techniques, the various controls or knobs that a PA would have, which it's gate bias as well as the way the inputs are configured, we are able to improve the efficiency of the PA, especially across temperature, across process corners, and across signal conditions. And we have some very good IP that we are proposing to our customers, which we hope to take into production soon. Similarly, on FR2, like I mentioned, our beamformers are using silicon germanium technology, which is slightly higher power supply, which ekes out a little bit more efficiency, while we have a lot of innovations in the TR switch as well as the power amplifier circuit architecture in itself to improve the efficiency.
What are the trade-offs in semiconductor technologies used in PAs? For example, silicon, gallium arsenide, LDMOS, gallium nitride.
So clearly, I have kind of mentioned a few of the technologies that are used for the power amplifiers. And the technology of choice depends on a combination of many things. The frequency that you are trying to use, whether it's millimeter wave or FR1 frequency, the power level that you're trying to get out of your power amplifier, what you expect your junction temperatures to be, for example, and the current densities. And each of these technology has its own play. all the way from bulk CMOS technology to silicon germanium to also what we call as the RF SOI technologies. These are all silicon technologies, and generally they tend to kind of do very well at lower output powers and at higher frequencies of operation. As you graduate to slightly higher output powers and maybe not as high frequency of transmission, when we are talking more of FR1, then gallium arsenide starts to play a good role, where you are getting into more than, like, for example, 2 watts of saturation power, or the peak power that you want to transmit out of a PA. Gas tends to start take a better foothold compared to silicon technologies that I mentioned, because of the better breakdown voltage that gas has, while having decent GM as well as FT, Fmax out of those transistors. And when you really go into much higher output powers, typically used in wireless infrastructure applications or macro base stations, then you tend to see more of LDMOS and gallium nitride, where you are able to get much higher breakdown voltages to support the higher supply and higher output powers that you need to drive out of these power amplifiers. So every technology has its own merits, and it depends on the particular application at hand on what technology you use.
Naveen, thank you for your time. This is Martin Rowe signing off for 5G Technology World. Thank you for watching.